Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallics in catalysis and biology, and in this series of lectures we have looked into various reactions that are important to catalysis, particularly from the industrial perspective in terms of industrial scale synthesis, and we have been looking at the applications of organometallic chemistry in a big level. Now, in this series of lectures, in the last few lectures we have looked into olefin metathesis, particularly alkene metathesis reactions. We have looked at how it was developed, the story behind their development, discovery, development, mechanisms, and also the various types of metathesis reaction that have been subsequently discovered and are put under same umbrella as the class of metathesis reaction. Continuing further along this discussion, we are going to be discussing another important topic, variant of metathesis reaction, particularly the cross metathesis reaction. The cross metathesis reaction is given by the following equation. And it is represented by so this is a sort of intermolecular metathesis reaction. So, intermolecular version of metathesis reaction. Now, these cross metathesis reaction, the applications of cross metathesis reaction is significant, and the development of cross metathesis reaction for industrial purpose application is also very interesting. Now, let me just give a brief overview or the story about how this cross metathesis reaction came into being, particularly for utility in industrial scale applications. Now, these all began back in 1960s or 70s, 60s, particularly when people were trying to make this large scale synthesis of olefins. Now, the story starts with the need for developing soft detergents, need for developing soft detergents which are nothing but linear chain linear fatty alcohols as opposed to hard detergents which are branched fatty alcohols. Now, these branched fatty alcohols, they were sort of being sold by Shell, by Shell development Shell chemicals, and these hard detergents or branched fatty alcohols, a long chain alcohol branched long chains with alcoholic ends. These are called long fatty alcohols. They were causing a lot of depositions of foams and on the rivers, the foams and surfactants on the rivers, and it was sort of creating a biological ecological havoc. And there was a need and because of lack of any method for their degradation, there was a need to develop the soft detergents having linear fatty alcohols. So, that is how the story starts, and fatty alcohols that time were in high demands and had a lot of market potential. So, they were in high demands with a lot of market potential. So, the idea was to access this long chain fatty alcohols, and they primarily were being produced from hydroformylation from alkenes in presence of chlorine to give long chain alkanes, to give alkyl halide that would undergo HCl elimination to give olefins, and that olefins under hydroformylation and then subsequently a reduction would give these fatty alcohols, both linear and the branch. So, that was the method at that point of time which was being used for producing these soft and hard detergents which were obtained from the fatty alcohols. Now, the other way of accessing these olefins are from cracking petroleum, large scale cracking of natural oil, natural gas. So, so there was sort of a demand, to go all the way from olefins to these detergents via this alkyl halide, then olefins, and then hydroformylations, and so on, so forth. This is alkanes. Okay. Now, at that point, the Shell Chemical discovered Shell higher olefin polymerization process, which is called Shell higher olefin process. So, what is this method? This method actually converted ethylene to alpha olefins, not alpha olefin oligomers and not polymers. And the catalyst used for this is nickel. Nickel was found to produce alpha olefin polymers from ethylene. But the other process also went on to become a very big industrial hit and even won a Nobel Prize, and this is Ziegler-Natta polymerization. If same olefin, if it is taken with titanium and aluminum halides, then it can make polyolefin polymers. So, Ziegler-Natta will take olefin all the way to polymer, whereas the need was to develop alpha olefin oligomers. So, they are not too high of a molecular weight, and that was developed by this shell higher olefin process by Shell Chemicals. So, this is a industrial process which would stop the polymerization of olefin all the way to polymer and could isolate them in oligomers. This was indeed a big discovery, and then what is important was that these oligomers that were being produced by shell hydrolefin had several fragments, it was a mixture of oligomers, and then they were at a stake in trying to find out how to utilize all of the fractions of these oligomers. So, to best illustrate the point, when they were looking at the concentration of alpha olefin produced. So, this is the mole percent of alpha olefin produced versus carbon number. The distribution was like this. This is called Schulz Flory distribution. Of alpha olefins produced from a shop process. So, what they observed that there is a large amount of alpha olefins are produced which are lower than C12 fragment. This is C12 fragment, and there is also large much less number of olefin produced which was above C18 fragment. Now, this was the distribution. Now, what was important over here is that from this distribution only this bottom part from C12 to C14 was of importance for detergent range. For with them they could make and tap this detergent. So, the middle portion, so there was no control for swap process, and it could give a lot of alpha olefins which are less than carbon 12 atoms, and then there would be a substantial also which are more than carbon 18 atoms, which had no use for detergent purpose. And the overall focus then was in how to use these two fractions. How to use these two fractions, and this whole story was developed in Shell, and what the idea was that this is where they took the help of other chemistry. So, the strategy was first these alpha olefins of less than C12 fragments and greater than C18 fragments to be isomerized fractions to be isomerized. That means that for example, if there is an alpha olefin it would have somewhere in the middle the olefinic bond getting isomerized with the total number of N being remaining the same. So, some sort of isomerization of the olefinic bond from alpha position to some internal position, that is what they looked at. And then the next strategy was metathesis, then to perform metathesis of these isomerized less than C12 and greater than C18 fractions. Now, the idea is that if these two fractions are done metathesis of, then they would give products which would be in this range, and again that can be used for detergent purpose. So, this was really a very clever way of utilizing the olefins which are supposedly non-usable at that point of time, and hence the idea was that for them to do isomerization followed by metathesis, which will give fragments again in this range of C12 to 18, and then they can further use it for the purpose for which the plant was built. And this is best illustrated in the following slide. For 1 octene and this is C8 fragment undergoing isomerization to give 4 octene and similarly CH217, this is called 1 echiocene, EICOACNE, this is C20 fragments undergoing similar isomerization to give C8, C8, this is called 10 eicosene fragment, which after isomerization would be subjected to metathesis to give C10 C14 fragment, which is called 2 tetra decene. So, and this is a C14 fragment. So, what is interesting to note is that in industrial scale, by taking the less than C12 and greater than C18 fragments, for example, 1 octene with C8 and 1 eicosene with C20, then undergoing isomerization giving this C8 and C20, which would undergo metathesis to give the C14 fragments, and this is in the middle for use for making the detergent reagent. So, this is a very nice way of utilizing in the alpha olefins which were unusable at that point of time. Now, what is important over here to note is that fact that both of these olefins are synthesized from ethylene using Schropp cell higher olefin process. So, now if somebody what Shell wanted to do is to apply 3 chemical reactions in industrial scale, and the 3 chemical reactions all in a same plant, and 3 chemical reactions would thus be now this is number 1, then isomerization number 2 and metathesis number 3. All of these should occur without interfering with in any of these, and then give the right product. And we have seen that the metal used for each of these are different. For example, for the first step it is nickel, whereas for the metathesis step it was ruthenium. So, there is a lot of optimization that they had to undertake in order to bring compatibility of 3 large scale processes, 3 different chemical reaction, and then in an industrial scale to be able to produce the fragment they need. Now, these in today's lecture what is important is that this metathesis reaction what they would be carrying out over here is nothing but cross metathesis. This metathesis reaction is actually a cross metathesis between 2 different olefins. That is exactly what we are seeing it. So, this Schropp process containing cross metathesis is a large scale industrial applications of Schropp as well as of metathesis chemistry. Now, towards this end a lot of research has to taken place. There were people expert in Schropp chemistry, developing Schropp chemistry, then people expert in isomerization chemistry as well as people expert in metathesis chemistry were put in place to come up with a single flow diagram in which this whole sequences that has drawn out here could be realized in an industrial scale, and that led to the following flow diagram for the Schropp production plant, which is shown over here. And that is given by first the ethylene feed, so that would enter the oligomerization chamber, then that would lead to a second chamber which would be used for catalyst recycling. So, the nickel catalyst used for Schropp would be recycled back for next phase, then comes the distillation chamber, which will give alpha olefins for market, and these would be C12 to C20 fractions, C18, C12 to C18 fractions, they would be straight away used for market. And then the remaining fractions which are less than C12 and greater than C18 would be taken to the fourth chamber, which will involve isomerization, and then post isomerization the next what remains is cross metathesis, and this would of less than C12 and greater than C18 fractions, and then finally the product would be C11 to C14 fractions for hydroformylation and benzene alkylation. So, the next formats would be used for that, and the remaining, the smaller one would again be recycled, which is less than C10 and greater than C14 olefins. So, this is a nice demonstration how the need for detergent or the need for detergent grade alpha olefins led to development of three important major industrial reaction all being carried out in a plant, and this was developed by Shell Chemical, and a nice article about this perspective development has been given by Wilhelm Kaim, who had been witness to this development of shop from the from their industrial research to that of the industry when he was working at Shell Chemical, and has given a nice account in Angiochem International edition 2013 52 12492 to 12496. So, with this I come to the conclusion of today's lecture, which was on cross metathesis, particularly with regard to the applications of cross metathesis, and in this perspective we have taken up the whole developmental story of cross metathesis reaction with respect to Shell hydroolefin process, which was developed at Shell Chemicals, and the whole perspective given from Professor William Kaim in the perspective given in Angiochem International edition 2013 volume 52 12492 12496. This is an excellent read. I suggest all the students of this class to refer to this article and to see how the need has led to interesting development, and here it was one which was done at industry, where 3 big reactions were put in place for large scale production to arrive at the need of what they wanted, which was about for mid range alpha olefins. So, with this I conclude today's lecture, and I look forward to discussing more on various application aspects of cross metathesis reaction when I meet next. Till then, thank you and goodbye.